In this video, we'll look at problem 2 on the 2026 E&M exam. So we're told that we have two non-conducting charged rods with uniform linear charge density lambda, and we can see that rod T is oriented vertically right here, and rod S is oriented horizontally here. And so in part A, what we're being asked to do is to find the electric field due to both rods at point P and at the origin O. So let's begin by considering point P. The difficult way to do this problem is to directly compute the electric field due to each rod. This is obviously a worthwhile exercise to do, but we can do much better. So what we're going to do is consider symmetry. We know that the contribution due to each opposite component of the rod, so I'm breaking down the rod into little points. Each of those points would produce an electric field contribution pointing along this line, pointing radially outward. And so we can see that these add up to a line pointing along the x-axis. You don't need to go through this full thought process. You can simply say, we're along the midpoint of a uniformly charged rod. Therefore, I expect the field due to rod T to point in the negative x direction. Then, for similar reasons, the field due to rod S points upwards. And so our overall resultant points diagonally to the left and up. So what are we actually showing in figure 2? We're just showing the total result. So that is what our electric field will look like. Next, let's apply the same logic to the origin. So what we can see is that the field due to rod T points straight down. The field due to rod S points to the right. Again, in this case, because we're proceeding radially along the axis of each rod. And so the resultant will point to the right and downwards, which we can indicate right there. Lastly, we're asked to draw an arrow starting on the dot that indicates the direction of net acceleration, A naught, of a small negatively charged sphere immediately after the sphere is released from rest at the origin O. So what we want to recall is that negative charges move opposite our field lines, and therefore the acceleration of our negative charge will be opposite that of the field at the origin. So part B is asking us to actually derive an expression for the magnitude of E naught at the origin due to both rods. So let's first grab our diagram. So here's our diagram, and as we discussed earlier, there are going to be two contributions of the electric field at the origin, namely the electric field due to rod T and the electric field due to rod S. So the first thing we'll note is that both of our rods have equal length, are at an equal distance from the origin, and have the same charge density. So all we need to do is to find the magnitude of one of those electric fields, and then we'll automatically have the magnitude of both. Magnitude of ES is equal to magnitude of ET, and we can avoid doing the same problem twice. So let's focus on finding the electric field of rod S. So we've got a rod of length 2L, negligible thickness, although my diagram isn't really indicating that. Then an additional distance L away from that, we've got the point at which we want to know the electric field, namely the origin. And so we're told specifically that we want to start from a fundamental physics principle or an equation from the reference information. So if we jump to the reference sheet, let's have a look at what seems relevant. So looking at our reference sheet, recall that what we're looking for is to find the electric field of our rod. And so that seems to be a case of us wanting to integrate the electric field along a charge distribution. So that's going to be our starting point. So let's write that down. Our starting principle is going to be that E is equal to 1 over 4 pi epsilon naught integral dq over r squared, r hat. Okay, what does this actually mean? The general principle here is as follows. Our starting point is the electric field of a point charge. As we know, the electric field of a point charge is E is equal to K, or 1 over 4 pi epsilon naught, Q over R squared. and then r hat indicating the radially outward direction. So what we're saying here is take our rod, let's break it up into infinitesimal charges, which we will label dq. For each of those infinitesimal charges, I can say that my infinitesimal contribution to the electric field dE is equal to 1 over 4 pi epsilon naught. And then dq represents my charge over r squared, r hat. And then we'll add up the electric field contributions of each of those infinitesimal charges. But with that, let's break down our process. So for each dq, I'm going to diagram out. I'll indicate that this is the distance of my charge from the point at which I want to compute the electric field. I'll also note the direction of r hat. So r hat is the unit vector pointing from my charge to the point at which I want to know the electric field, right? So in theory, here I've got r hat. But as we can see in this case, r hat is simply equal to x hat everywhere. So that allows me to start simplifying. I'm going to say that E is equal to just x hat. We can take that out of the integral. It's not dependent on my dq over 4 pi epsilon naught integral dq over r squared. And so now the question is r different for different dqs? Can we integrate this? R is a function of q, but not in a way which we can explicitly write out. And this is where our density becomes important. The density allows us to rewrite dq as a function of position. Specifically, we have a uniform density lambda, and by definition, this is equal to dq by dl, dl representing arc length. Moreover, in this particular case, I can say that my arc length is aligned along the x-axis, so dl is in fact dx. Great, so we can now rewrite this as, x hat out front over 4 pi epsilon naught, integral, and I'll replace dq with lambda dx over r squared. Last step, I now need to rewrite r as a function of x. To do this, I need to introduce where x equals 0 is located. So I'm going to go ahead and label, let's just get rid of some distractions there. I'm going to go ahead and label my origin. I'm going to choose to make x equals 0 be at our actual origin, indicated in the diagram. With that, I will claim that r squared is the same as x squared. And make sure that you understand why that's the case. So what we have now is lambda dx over x squared. But then let's think about our bounds of integration. Our bounds of integration are integrating along the rod. We start off at this edge of the rod, which is negative L, and end up at this edge of the rod, which is at negative 3L. Okay? And so our bounds of integration will be from negative 3L up to L. Let's go ahead and integrate that. So what we get is x hat over 4 pi epsilon naught times lambda, which is a constant. Integral of x to the negative 2 becomes negative 1 over x. And we're now going to evaluate from negative 3L up to negative L. So that becomes lambda x hat over 4 pi epsilon naught. 1 over L, negatives cancel out, minus 1 over 3L, which we can simplify lambda x hat over 4 pi epsilon naught, 3 minus 1 over 3L. And so what we now have is the electric field due to rod S. So electric field of rod S is equal to lambda over 2 pi epsilon naught L in the direction x hat. All right, remember what our goal was. Our goal was to find the total electric field, specifically the total magnitude of the electric field at the origin. As we said, this is not equal to ET. ET points in the other direction. ET is going to be equal to lambda over 2 pi epsilon naught L, but in the negative y hat direction, pointing downwards. If I'm looking for the overall magnitude of the electric field, remember that these are pointing at right angles to each other. And so all we need to apply is Pythagorean theorem, lambda over 2 pi epsilon naught L squared times 2, right? Since they're both identical, square rooted. And so what that leaves us with is simply square root 2 lambda over 2 pi epsilon naught. And that is our final answer for the magnitude of the electric field. So in part C, we're told rod T is removed, so we're just focusing on rod S, and rod S is beginning to move along the x-axis with speed v. We're then asked to sketch, importantly sketch, a graph of the electric potential V naught at the origin due to rod S as a function of the distance between the origin and the right end of rod S. So it may seem like the speed v is important, but note that all we care about is what is the potential when the rod is a distance r away from the origin. That should not have any dependence on speed. So kind of a distracting point put in there by the College Board. Note that we could go ahead and directly compute what our potential is as a function of r, and that is a worthwhile exercise, which I may do in a separate video if anyone asks for it. But we're simply asked to sketch, and when we're asked to sketch, all we need to really do is think about limiting cases, and maybe a bit more. So the first thing I'm going to note is that when the rod is right at the origin, the potential should essentially be infinite because we've got charges a distance 0 away from the origin. So I'm going to expect a vertical asymptote right there. Secondly, I'm going to expect that as we go infinitely far away, our potential approaches 0, and that's kind of enough for me to draw a rough sketch with no need to do the full integration. So now let's jump to part D. So in part D, we're told that, okay, we've now added a rod W with opposite charge density to rod S, negative lambda instead of lambda, and we're asked the same question. It is also moving with speed v, so both are retreating at the same rate, and we're being asked to find the potential at the origin as a function of our distance. And so the key here is realizing the following. The potential of rod W is exactly opposite that of rod S. Potential is a scalar quantity, so we don't need to worry about differing directions. So VW is equal to negative Vs. And since they have the same speed, they'll have the same distance at any point. And so for that reason, our total V naught, which is equal to VW plus Vs, will be 0 no matter the distance of both rods from the origin. And so what we would have is just a flat line along the x-axis. And with that, we finished up problem 2.